Hello everyone, my name is Sonia Lamba. I am from ABES Engineering College and today we will discuss the various multiple access protocols. These are the topics that we are going to discuss today. We will discuss the subdivision of the data link layer into two sublayers. We will discuss the various multiple access protocol, and among these protocol, we will discuss one of the category known as the random access protocol, and we will discuss the pure and slotted aloha, their vulnerable time, their efficiency, and their throughput. So here we can see that data link layer is subdivided into two sublayers. One is known as the one is known as the data link control and another one is known as the MAC sublayer. This is said to be the MAC sublayer, media access resolution layer. So some of the responsibilities of data link layer are now handled by the data link control layer and some are handled by the multiple access resolution. This MAC sublayer is originally designed to handle the access of the channel among the devices. Whenever the channel is shared and the multiple devices are using the shared channel for the transmission of the data, so which device will give the access to transmit the data using the channel will be decided based on the multiple access protocols provided by this MAC sublayer. So whenever the channel is shared and multiple devices are using the shared channel for the transmission of the frame, then this MAC sublayer is used to coordinate the access among the devices. But if the channel is not shared, if the channel is point to point, it means the channel is dedicated between the two devices. So we are not going to use this sublayer. But if channel is shared, definitely we need to coordinate the access among these devices so that they can access the channel and can reduce the number of collisions. So at that time we need some media access control protocol, and this is the layer that will provide the media access protocols. So here we have the categorization of multiple access protocol provided by the MAC sublayer. So first category is the random access protocol. Among this category, we have the various protocols known as Aloha, Pure Aloha, Slotted Aloha, CSMA, Carrier Sense Multiple Access, Carrier Sense Multiple Access Collision Detection, Carrier Sense Multiple Access Collision Avoidance. Second category is the controlled access protocols. In this category, we have the three techniques known as reservation, polling, and token passing. And in the third categorization of multiple access protocol, we have again the three techniques known as FDMA, frequency division multiple access, time division multiple access, and code division multiple access. All these are the multiple access protocols, and these are the techniques or the protocols that will coordinate the access among the devices for transmitting the data when the channel is shared. So first we will discuss the various random access protocol. Random access protocols are also known as the contention based methods. So first we will discuss why these protocols are said to be the random access. So these are called random access because there is no scheduled time at which the device will send the data. Whenever the device is having the data to send, device can immediately send the data over to the channel. That's why these protocols are called random access. Now, these protocols are also known as contention based methods. Now, these are called contention based because here the devices are competing with one another to access the medium for the transmission of the frame over to the shared channel. Because the channel is shared and the multiple devices are using the shared channel, so each device will compete with one another. Because here we are saying that no device or no station is superior to the another station. All the stations that are using the shared channel are equal. No station can permit and no station does not permit another station to send. All stations are equal. No station is primary and no station is said to be secondary. All the stations are equal. All have the equal access of the channel. Because the channel is shared, these devices will compete with one another to access the channel for the transmission of the frames. So this diagram depicts the technique used behind the pure aloha protocol. So if talking about the pure aloha protocol was developed in 1970s at the University of Hawaii. Initially this pure aloha protocol was used by the wireless links, but now this can be used by any shared medium to access the to coordinate the access among the channel. So in this diagram we can see that we have the four devices or four stations that are connected with the shared channel is shared. Okay, so if we can see that here each station is sending the two frames, like station 1 is sending frame 1.1 and 1.2. Station 2 is again sending the two frames, frame 2.1 and 2.2. Station 3 is sending the frame number 3.1 and 3.2. Station 4 is sending the frame 4.1 and 4.2. So here we can see that the stations are sending the frames, but concept behind the pure aloha is whenever the station is having the data or the frame to send, station will immediately send the frame over to the channel. So in this case we can see each station altogether have sent 8 frames, but out of the 8 frames only 4 frames are able to reach the destination successfully. But these 4 frames, frame number 2.1, 1.2, frame number 3.1, and frame number 4.1, these 4 frames will collide with one another and will be discarded because of the collision. So out of the total 8 frames, 4 frames will successfully reach to the destination. So in pure aloha the basic idea or the basic concept is whenever the station is having the data to send, station will immediately send the data. So this is the diagram that depicts the idea used behind the pure aloha protocol. So this flow chart now tell us the procedure used for the wireless aloha protocol. So here we can see that pure aloha is the protocol that relies on the acknowledgement. It is the protocol that relies on the acknowledgement because in the previous diagram we have seen that some of the frames will collide, and then the frames that will collide with each other are discarded. So stations will again resend these frames. So here pure aloha protocol wants whenever the station receives the frame successfully, the receiver will send the acknowledgement to inform the sending station that the frame has been successfully reached. So because if either the frame or the acknowledgement has discarded and the or lost during the transmission, and station have no information, so whenever the timer timeout occurs, station will again resend the frame. But the point here is if all these stations will resend the frame again after a timer timeout occurs, so collisions will occur again. So to avoid the number of collision, to reduce the number of collision, we need to include some randomness between the transmission of this resending frames. So for that purpose we have included the back of time. We will discuss here the back of time, and we will keep our track on the number of attempts as well. It will not happen that the station will again and again resending the frames. The station will send the frame maximum to 15 attempts, and if in the 15 attempts the station is not able to send the frame successfully to the destination, then the station will wait for a longer period of time for retransmitting the frames again. So in this flow chart we can see that here we will start the number of attempt initially is 0 because a station first time is trying to sending the frame. Now station will send the frame and then will wait for the timer timeout occur. Station will send the frame and then we'll wait for the timer timeout occur. Timer timeout occur time will be calculated using this formula. Here we are multiplying the propagation time with 2, so that we can calculate the timer timeout. So station will wait for this period of time. If in before this period, if whether the acknowledgement has received, or if the acknowledgement has not received. If the acknowledgement has received during the timer timeout occur, it means the frame has been successfully reached to the destination. But if there is no acknowledgement from the receivers, and it means either the frame or the acknowledgement has been lost during the transmission. So in that case, we will need to resend the frame. So we have increased the number of attempts by one here. We will increase the number of attempts by one here. So here we will keep track on the number of attempts as well. So number of attempts right now is one. Is one. So which is less than kmax value is 15. So we are not going to abort the transmission. We will station will send a random number r between 0 to 2 to the power k minus 1 to calculate the back of time. Back of time will be denoted by TB, and TB is calculated either by the formula R into TP or R into TFR. R into TP is R is the random number that we have calculated here, and TP is the propagation time. Back of time is also can also be calculated using the formula R into TFR. Here TFR is the frame transmission time. So station will wait for this back of time. This station is waiting for this back of time to include the randomness, so that the stations again will not send the data at the same time. So that we can avoid or reduce the number of collisions. Now again, after this period of time, station will again send the frame, then wait for the timer timeout occur. During this timer timeout occur, if the acknowledgement has received, it means the frame is successfully reached. Otherwise, again we will increase the number of attempt. We will check whether it is less than kmax or not. If it is, then we will calculate the random number, and then again we will calculate the back of time, and then we'll after the wait of back of time, station will send the frame again. So this is the procedure behind the pure aloha protocol to reduce the number of collisions. Now, we will discuss the vulnerable time for the pure Aloha protocol. So, vulnerable time is the time during which there is the possibility of collision. So, here we can see we have the three stations: station A, station B, and station C. So, in this case, we are seeing that station B has started transmitting its frames at T minus TFR time, but station A has start transmitting its frame at time t, and station C has start transmitting its frames at t plus TFR time. So here we can see that the end of the frame sent by the station B will collide with the beginning of the frame sent by the station A, and the end of the frame sent by station A will collide with the beginning of the frame station sending by station C. So here we are seeing here we can see that this is the vulnerable time. This is the vulnerable time during which there is the possibility of collision. So if during this period of time station will not send any of the frame, so definitely the frame sent by station A will successfully reach to the destination. So this is the vulnerable time in case of pure Aloha 2 into TFR. Here TFR is the frame transmission time. If a station will, or if all other stations will wait for this period of time, so definitely the frame sent by the station A will successfully reach to the destination. So that's why this is the time during which there is a possibility of collision, and this is the vulnerable time in case of the pure Aloha protocol. So now talking about the throughput and the efficiency provided by the pure Aloha protocol. So for calculating the throughput, we have this formula: S is equals to G into e to the power minus 2g. Here g is the average number of frames generated by the system during one frame transmission time. So this is the formula via which we can calculate the throughput for pure aloha. So pure aloha will gives us the best throughput when g is 1 by 2, and the efficiency provided by pure aloha protocol is 0.184. It means uh, out of all the frames sent by the stations altogether, maximum 18.4% percent frames will successfully reach to the destination. Rest other frames will collide with each other and then discarded. So this is the efficiency percentage provided by the pure aloha protocol, and this is the formula via which we can calculate the throughput for the pure aloha. Now we will discuss the slotted aloha as the multiple access protocol. Now the concept behind the slotted aloha protocol is here the time is divided into the time slots. And whenever the station is having the data to send, station will send the data at the beginning of the time slot only. If the station will misses this movement, then the station will wait for the beginning of the next time slot, and then in the next time slot only station will send the frame. So this is the basic concept behind the slotted aloha protocol. Here also we can see we have the 4 station, all are connected via the shared channel, and all station together sending the 8 frames, but out of 8 frames only the 4 frames will survive, and rest 4 frames will collide with one another and then discarded. So this is the concept. We can say that this is the collision duration during which the frame collide with one another and then discarded. So in case of slotted aloha, the concept is station will not send the frames randomly. Station will wait for the beginning of the time slot, because here the time is divided into the time slots, and if the station will misses that movement, then station will wait for the next time slot only. But in the pure aloha, concept was station will send the frame whenever the station is having the data to send. Station will not wait for any movement to occur. Station there was the randomness. Station will send the frame immediately whenever the station is having the data to send. So this is the difference between the slotted and the pure aloha as the protocol. So here we can calculate the vulnerable time for the slotted aloha protocol. Here the vulnerable time is reduces in case of the slotted aloha. In case of slotted aloha, TFR, transmission frame time, is the vulnerable time. This is the time period during which there is a possibility of collision. If in this period if only one station will send the frame, then definitely there will be no collision, and this frame will successfully reach to the destination. Now, talking about the throughput and the efficiency of the slotted aloha protocol. So throughput in case of the slotted aloha protocol will be calculated using this formula: S is equals to G into e to the power minus G, where G is the number of frames generated during the one frame transmission time, average number of frames generated during one frame transmission time. And here the maximum throughput calculated is 0.36%. It means ki 0.36 maximum efficiency will be 0.36, and if we will calculate this efficiency in terms of percentage, so 36% frames will successfully reach to the destination, and rest frames will be discarded just because of the collision that has been occurred during the transmission. So, in case of slotted aloha, efficiency is maximum when G is 1 by 2. G is actually 1, sorry, 1. So, efficiency is maximum when G is 1. So, these are the references used for designing these slides as well as for preparing this lecture. Thank you everyone for patient listening.